Okay, how we doing, people? 1.3, know the equipartition theorem. So this will be a pretty short learning goal, but it will be impactful for this. We're going to take advantage of this theorem all semester, which states, in a sample of temperature T, so basically whatever our temperature is, call it T, all quadratic contributions to the total energy have the same mean value, which is 1/2 K Boltzmann times temperature. So what does all of this mean? Well, as we shall see in the coming videos, we can come up with rather complex ways of calculating what the population of a certain state is based on its temperature. And that's not a simple calculation. However, the equipartition theorem gives us a little bit of a shortcut or a quicker way of assessing what the population of, and as we shall see specifically, translations and rotations. Okay? So we can get a quick assessment of the kinetic energy or even the temperature contributions due to translations and rotations. So imagine that we have a simple atom. So this could be a likely a noble gas, right? We're not talking about a molecule, just a very simple atom. Well, we know that atom is free to move in 3 dimensions. And if we write its kinetic energy from classical physics, we know that it's going to be related to 1/2 mv squared. And if we consider all 3 dimensions here, we know we're going to have components in the x, we're going to have components in the y, and we're going to have components in the z. And so all 3 of these, this actually gives us 3 contributions to the mean energy. Okay. So 3 in each, or 1 in each dimension, giving us 3 in total. So we could, of course, calculate the kinetic energy of our simple atom with knowledge of its mass and its velocity. However, if we don't know its velocity or we don't have a good way of assessing that, we can use this shortcut, this estimation in the equipartition theorem. So we will get a contribution of 1/2 kBt for each of these quadratics. Well, each one of these represents a quadratic, so that means we have 1/2 K Boltzmann times temperature plus 1/2 K Boltzmann times temperature plus another 1/2 K Boltzmann times temperature. And if we add all of those up, as you can see, we get 3/2 K Boltzmann times temperature for the kinetic energy of a simple atom as a function of temperature. So, this would have units of just joules, right? The unit of K is joule per molecule per Kelvin, so, times the Kelvin in temperature. So this will just give us joule per molecules. And as we're going to start learning in our calculations, we can replace K Boltzmann with R, the universal gas constant, and in this case, we would want that to be 8.314. And that's going to give us joules per mole, which of course we could scale up to kilojoules per mole to give us a realistic view of what the kinetic energy is of a simple atom moving in 3 dimensions. And as it turns out, at room temperature, so I'll say T room, this is approximately equal to 4 kilojoules per mole. I'm only giving you that in 1 sig fig, so we can calculate that in more details. But the way that this now will connect to our molecular modes is at room temperature, we have 4 kilojoules per mole of available thermal energy. That's how much energy we have in a room at room temperature. So we're going to see this deep connection between what the temperature of a sample is and the available energy we have stored in its molecular modes. Okay, so that's it for this one. I told you it was going to be a short one. We're going to get into the more complicated math that I mentioned in the coming videos.